To calculate the total volt-amps demand for a service with multiple motors, you need to consider the volt-amps of each motor individually, taking into account factors like the number of phases, voltage, current, and duty cycle. Here's a step-by-step guide. Firstly, calculate the total volt-amps for the three-phase motors. For each three-phase motor, you'll use the formula volt-amps equals volts times amps times 1.732, which is the square root of 3. Let's say you have three motors that are 480 volts three-phase. You have the first motor with a nameplate current of, let's assume, 14 amps. The second motor is 14 amps as well. The third motor is, let's say, 7 amps. Now calculate the volt-amps for each motor. For the first motor, volt-amps equals 480 volts times 14 amps times 1.732, which equals approximately 11,667 volt-amps. For the second motor, since it's the same specifications, it will also be 11,667 volt-amps. For the third motor, volt-amps equals 480 volts times 7 amps times 1.732, which equals approximately 5,833 volt-amps. Now, sum up the volt-amps for all three-phase motors. 11,667 volt-amps plus 11,667 volt-amps plus 5,833 volt-amps equals 29,167 volt-amps. Secondly, calculate the total volt-amps for the single-phase motors. For each single-phase motor, use the formula volt-amps equals volts times amps. Let's assume you have three single-phase motors operating at 240 volts and one operating at 120 volts. For the first 240 volt motor, let's say it draws 6 amps. For the second 240 volt motor, let's say it draws 8 amps. For the third 240 volt motor, let's say it draws 4 amps. And the 120 volt motor, let's say it draws 10 amps. Calculate the volt-amps for each motor. For the first 240 volt motor, volt-amps equals 240 volts times 6 amps, which equals 1440 volt-amps. For the second 240 volt motor, volt-amps equals 240 volts times 8 amps, which equals 1920 volt-amps. For the third 240 volt motor, volt-amps equals 240 volts times 4 amps, which equals 960 volt-amps. For the 120 volt motor, volt-amps equals 120 volts times 10 amps, which equals 1200 volt-amps. Sum the volt-amps for all single-phase motors. 1440 volt-amps plus 1920 volt-amps plus 960 volt-amps plus 1200 volt-amps equals 5520 volt-amps. Thirdly, adjust for the duty cycle. The duty cycle refers to the percentage of time the motor is operating compared to the total time. If a motor operates for a shorter period, you can reduce its contribution to the total volt-amps demand. Let's say one of the 240 volt motors has a 15-minute duty cycle, and the 120 volt motor has a 30-minute duty cycle. This means the 15-minute duty cycle motor only operates for 15 minutes out of every hour, and the 30-minute duty cycle motor only operates for 30 minutes out of every hour. Convert the duty cycles to percentages. A 15-minute duty cycle is 15 divided by 60, which is 25%, or 0.25. A 30-minute duty cycle is 30 divided by 60, which is 50%, or 0.5. Adjust the volt-amps for the motors with duty cycles. The 240 volt motor with a 15-minute duty cycle has a calculated volt-amps of 1440 volt-amps. Adjusting for the duty cycle, we multiply 1440 volt-amps by 0.25, which equals 360 volt-amps. The 120 volt motor with a 30-minute duty cycle has a calculated volt-amps of 1200 volt-amps. Adjusting for the duty cycle, we multiply 1200 volt-amps by 0.5, which equals 600 volt-amps. Recalculate the total volt-amps for single-phase motors with the adjustments. So the new calculation is 360 volt amps plus 1920 volt amps plus 960 volt amps plus 600 volt amps equals 3840 volt amps. Fourthly, add all the volt amps values together. Now, sum up the total volt amps for both three-phase and single-phase motors. 29,167 volt amps for the three-phase motors plus 3,840 volt amps for the single-phase motors, which equals 33,007 volt amps. Therefore, the total volt amps demand for the service is 33,007 volt amps. Keep in mind some additional notes. Make sure you are using the correct voltage and current values from the nameplates of the motors. The nameplate provides accurate values for your calculations. Consider other factors that might affect demand, such as power factor or harmonics. Power factor is the ratio of real power to apparent power, and harmonics are distortions in the current or voltage waveform. These factors can affect the overall demand on the service. Double-check all your calculations carefully for any errors. Even small errors can lead to significant discrepancies in the final result. Here's a recap of the formulas. For three-phase motors, volt amps equals volts times amps times 1.732. For single-phase motors, volt amps equals volts times amps. For duty cycle adjustments, adjusted volt amps equals calculated volt amps times duty cycle percentage. By following these steps and tips, you can accurately calculate the total volt amps demand for a service with multiple motors, ensuring that the electrical system is properly sized and can handle the load. It's important to have accurate information from the motor nameplates, including voltage, full load amps or FLA, and any service factor information. The service factor is a multiplier that indicates how much a motor can be overloaded for short periods without damage. If a motor has a service factor greater than 1.0, you may need to adjust the full load amps value for your calculations. Also be aware of the motor's starting current. Motors draw a significantly higher current when starting compared to their running current. This inrush current can be several times the full load amps. If multiple motors start simultaneously, it can cause a large voltage drop and potentially overload the service. To mitigate this, consider using reduced voltage starters or staggering the motor start times. Another factor to consider is the efficiency of the motors. Motor efficiency is the ratio of mechanical power output to electrical power input. A less efficient motor will draw more current to produce the same amount of mechanical power. The motor's efficiency is usually indicated on the nameplate. You can use the efficiency value to calculate the actual power consumed by the motor. For example, if a motor is 90% efficient, it means that 90% of the electrical power it consumes is converted to mechanical power, while the remaining 10% is lost as heat. When calculating the total demand, it's also essential to consider any other loads on the service, such as lighting, 8-track, and other equipment. These loads should be added to the motor load to determine the total demand. It's also essential to consider the National Electrical Code, or NEC, requirements for motor circuits. The NEC provides guidelines for sizing conductors, overcurrent protection, and other components of motor circuits. It's important to consult the NEC to ensure that your motor circuits comply with the applicable regulations. For example, NEC Section 430 covers motors, motor circuits, and controllers. It provides specific requirements for motor overload protection, short circuit protection, and conductor sizing. NEC Table 430.52 provides guidance on selecting the appropriate size of overcurrent protection devices for motor circuits. NEC Table 430.248 and 430.250 provide the full load currents for motors based on voltage and horsepower. These tables can be helpful if the motor nameplate is not available or if you need to verify the nameplate information. Additionally, the power factor of the motors can impact the overall system demand. A low power factor can increase the current drawn from the source, leading to higher losses and reduced system capacity. If the power factor is significantly low, consider using power factor correction capacitors to improve the power factor and reduce the current. Harmonics are another factor that can impact the system. Harmonics are distortions in the current or voltage waveform, and they can be caused by nonlinear loads such as electronic devices and some types of motors. Harmonics can cause overheating of equipment, increased losses, and interference with other equipment. If harmonics are a concern, consider using harmonic filters to reduce the harmonic content of the current. It's also important to consider the ambient temperature when sizing motor conductors and overcurrent protection devices. The ampacity of conductors decreases as the ambient temperature increases. NEC Table 310.15 provides ampacity correction factors for different ambient temperatures. Be sure to apply the appropriate correction factors to ensure that the conductors are properly sized for the application. Furthermore, consider the altitude of the installation. At higher altitudes, the air is thinner, which can reduce the cooling capacity of motors and conductors. This may require derriting the motor or increasing the conductor size. Another important consideration is the type of motor being used. Different types of motors have different characteristics such as starting torque, speed regulation, and efficiency. The type of motor will impact the design and selection of the motor circuit component. For example, induction motors are commonly used for general-purpose applications, while synchronous motors are used for applications requiring precise speed control. When calculating the total demand, it's essential to account for any future loads that may be added to the service. It's a good practice to provide some spare capacity to accommodate future growth. This will prevent the need for costly upgrades in the future. Also, ensure that the service equipment, such as the transformer and switchgear, is adequately sized to handle the total demand. The service equipment should be rated to handle the maximum load that may be imposed on it. Consider the diversity factor when calculating the total demand. The diversity factor is the ratio of the sum of the individual maximum demands of the various loads to the maximum demand of the entire system. It accounts for the fact that not all loads will operate at their maximum demands simultaneously. Using a diversity factor can reduce the required size of the service equipment. In addition to calculating the total volt-amps demand, it's also important to calculate the total current demand. The current demand is used to size the conductors and overcurrent protection devices. The current can be calculated by dividing the volt-amps by the voltage. For three-phase circuits, the current is calculated as volt-amps divided by volts divided by 1.732. For single-phase circuits, the current is calculated as volt-amps divided by volts. Remember to use the appropriate voltage for the calculation, which is typically the line-to-line voltage for three-phase circuits and the line-to-neutral voltage for single-phase circuits. Furthermore, it is crucial to ensure that all electrical work is performed by qualified and licensed electricians. Working with electricity can be dangerous, and it's important to follow all safety precautions to prevent accidents and injuries. Always energize the circuit before working on it, and use appropriate personal protective equipment, or PPE, such as gloves and safety glasses. In addition to the NEC, there may be local codes and regulations that apply to motor installations. Be sure to check with the local authorities to ensure that your installation complies with all applicable requirements. Accurate and thorough documentation is crucial for any electrical installation. Keep detailed records of all calculations, equipment specifications, and wiring diagrams. This documentation will be helpful for future maintenance and troubleshooting. It is important to label all electrical equipment clearly and accurately. Labeling helps to identify the equipment and its function, which can be helpful for maintenance and troubleshooting. Use permanent labels that are resistant to fading and damage. Finally, regular maintenance is essential for ensuring the safe and reliable operation of motor circuits. Perform regular inspections of the equipment and address any issues promptly. This will help to prevent failures and extend the life of the equipment. Also, ensure that the motor is properly lubricated and that the ventilation is adequate. Overheating and lack of lubrication are common causes of motor failure. In summary, calculating the total volt-amps demand for a service with multiple motors requires careful consideration of several factors, including motor voltage, current, duty cycle, power factor, harmonics, and applicable codes and regulations. By following a systematic approach and paying attention to detail, you can ensure that the electrical system is properly sized and can handle the load safely and reliably. Always consult with qualified professionals when designing and installing electrical systems. They have the knowledge and experience to ensure that the installation is safe and compliant with all applicable requirements. By considering these factors, you can accurately calculate the total volt amps demand and design a safe and reliable electrical system.